I'm sure we've all seen the science museum demo or the visualization in an image of how general relativity works, right? General relativity, the curvature of space-time, matter and energy tells space-time how to bend, and the bending of space-time tells matter and energy how to move. And so we might see a picture where there's like a grid system, and then there's something plunked in the middle like a star or a black hole or a planet or whatever, and it looks like all of this grid system is curved down around the vicinity of that object. Or we've gone to a science museum, or we've seen a physics class demo where they've stretched a flexible sheet over a frame, and then you drop something heavy like a bowling ball in the center, and the sheet bends down, and then you can flick little ping pong balls around. You see their trajectories get altered, like they'll go straight and then go flying off. And that's all great. There's nothing wrong with that, except there are some things wrong with that. And what's wrong with those demos, it's not necessarily that they're wrong, as in they're telling you lies. It's that they're not entirely complete in their description of general relativity, and they can lead to some potential misunderstandings. Because what you're seeing in that demo or the picture or the visualization is a two-dimensional surface, like the surface of that flexible sheet, being bent down into a third dimension. And so people immediately ask, well, hey, our universe, we have three spatial dimensions. So if there's an Earth or a star or a black hole or whatever over there, what is our space bending into? Is it bending into a fourth dimension? Is there like a fourth dimensional down that everything's bending into? And it's a little bit tricky to describe what's really going on, because what's really going on is encoded in very complicated mathematics that aren't easy to describe. So usually we retreat to a metaphor and just leave it at that. But I think you guys are beyond metaphors here. You can handle the real stuff. The geometry caused by gravity in general relativity is intrinsic, not extrinsic. It's built into the dimensions of space itself. It doesn't require any other higher dimensions. It doesn't require any external agents pushing or pulling or bending into. It's built in itself. It's a property of the fabric of space itself. Paths that initially start out parallel will converge or diverge or follow all sorts of complicated paths in 3 dimensions. And that's it. There doesn't have to be a fourth dimension that our own universe is embedded inside. So there can be, but there doesn't have to be. It's not needed for the mathematics to work. Curvature is an intrinsic property. It's built in to space. It's not because our space is embedded in something else. The second misleading thing that the typical demo or visualization misses is that general relativity is a curvature of space-time. The full 4-dimensional thing. You can't just leave off the time component and think you're A-okay. You will get the wrong answers. You have to curve the dimension of time in addition to the dimensions of space. And this works. One way to think about how this works is to talk about light cones. I know I haven't mentioned light cones a lot in this show, but now's as good a time as any. A light cone is the limit of where you can go, the range of where you can go, limited by the speed of light. So if I see a distant star and I want to go a distant star, I know I can't get there tomorrow. So my light cone restricts my movements in space-time. I can't be over at the star now. I can't be over at the star tomorrow. I can't be over at the star in a year. But if I crawl along, I can catch up to the star in its future and my future. Say, 40,000 years from now, I can eventually get to that star. Or if I'm a beam of light, I'll get there in 4 years. So the light cone is the limit of where I can go in space and time set by the speed of light. That determines the angle of the cone is the speed of light. So I like to think of, this is like the worst analogy possible, but I can't get it out of my head. I like to think of, when dogs have those collars with the cones on them, and imagine that limits their movement. So like they're walking and they have a limited visual capacity. They can't see stuff out to the sides. They can only see stuff in a cone, and this limits where they're going to go. So if there's a fire hydrant over here, they're going to miss it because they can't see it. But there's a fire hydrant over here within the cone, they can go there because it's within their doggy light cone. What gravity does, what a massive object does, is tilt a light cone. It tilts where your future trajectories can be. So if I'm a dog racing by the sun, I have a light cone, I have a range of places I'm allowed to go. But then I pass by a massive object like the sun, and say the sun's over here on my left, it's going to tilt my light cone. Now my range of possible trajectories are over here. So if there was something right on the edge, say there was a little, doggy treat or something like right on the edge over here. Originally it was in my light cone and I could get there in my future. But then because I passed by the sun, it passes out of my light cone range and I'm not going to get that doggy treat. Maybe there's a new doggy treat over there, a bigger one, a better one. We'll have a happy ending for the dog that's flying by the sun. Gravitating objects alter the light cones of objects passing by them. And this is important because it's what affects the trajectory of an object is the altering of the light cone path or a light cone direction and the static curvature of space itself. So when you see that museum demo or you see the visualization in a picture online or whatever, that is incredibly exaggerated. The static curvature of space that alters trajectories is much, much, much weaker than that. It's incredibly subtle. Otherwise, we would have noticed it, like 400 years ago. It took a lot of work to notice these very subtle deviations. And if you just include the static spatial curvature, you're going to get the wrong answers. You're not going to fully have a full and complete picture of gravity. You need to also include the altering of trajectories, the turning of light cones, which is curvature you can think of as curvature in the fourth dimension, the dimension of time. It alters what your future is capable of. And it's these two effects combined that give the full theory. So when we look at something like the deflection of light, when a little beam of starlight grazes the sun and its path gets bent, if you just think of the static curvature of space, you're only going to get half the answer. You're only going to get half the deflection you actually observe. To get the other half, you have to include the effects of tilting the light cone, and that gets you your full picture. It's this last part interesting. It's the static curvature of space that tripped up Einstein. He didn't think that space itself would be statically curved around a massive object like the sun. He thought it would just be the tilting of the light cone. And that little hitch got him stuck in developing general relativity for 2 years. And it took him 2 years to finally get over it and acknowledge that gravitating objects will have that static curvature of space around them, and that's eventually what got him to the full theory. So at least the museum demos and the visualizations are showing you the more difficult, non-obvious part that tripped up even Einstein for a couple of years. They're showing the static curvature of space, but they're not showing you the curvature of time, which is equally as important, and they're not showing you that curvature is intrinsic. It's built-in property of our four-dimensional space-time. It's not a property brought about by our embedding of our four-dimensional universe in a larger five-dimensional or higher dimensional structure. You don't need that. You don't need that. It's extra. It's junk. It's a waste of time. Just focus on the essentials. Curvature is intrinsic to our universe, and it's curvature of space and time that gives you the full theory. Thanks so much for watching. I hope you enjoyed this another edition of Ask a Spaceman. You can subscribe. Make sure you hit the notification bell thingy. I don't know which corner it is. It's one of these two. But look for the bell. Click it so you get notified when I go live every Thursday. Go to Patreon to help support me making more of these things. And I'll see you next time.